All right, let's get right into it. Welcome to this explainer. Today, we're cutting through the daily hype cycle to look at the deep philosophical debates that are actually driving the future of artificial intelligence. We're going to start with a concept that has completely defined the last decade of AI research, but as you'll see, modern developments are starting to radically challenge it.
Here is how we're breaking things down today. First, the first bitter lesson. Then, hitting the data wall. Third, finding new scaling axes. Fourth, the second bitter lesson. And finally, strategic implications.
Okay, part 1, the first bitter lesson.
So the crucial takeaway from Richard Sutton's foundational 2019 essay is this. Over 70 years of AI history, researchers who tried to hard-code human insight into machines eventually lost. They lost to researchers who simply scaled up search and learning. If you know your AI history, this is essentially a continuation of those classic debates. We're talking about Frank Rosenblatt's early learning-based connectionist models, eventually steamrolling the symbolic rule-based systems championed by folks like Marvin Minsky. Because it turns out, our human intuition often just gets in the way of scalable computing.
Sutton put it brilliantly with this quote: "As the cost of computation exponentially falls, thanks to Moore's law, simple, scalable solutions inevitably overtake complex, handcrafted human designs." You can actually trace this logic back to Claude Shannon's mathematical view of information. It fundamentally proved that general-purpose, scalable systems, ones rooted in statistical search and learning, simply process the world better than any abstraction a human could ever design.
And notice how this exact pattern played out across multiple, completely distinct fields. In chess, Deep Blue used massive search to crush specialized chess heuristics. In Go, AlphaGo Zero removed human expertise entirely, training strictly via self-play. Speech recognition completely abandoned handcrafted phonemes for statistical models. In computer vision, it tossed out explicit edge detection for convolutional neural networks. History has repeatedly proven that human knowledge hits a plateau, while compute just keeps scaling.
Which brings us to part 2. Hitting the data wall. Now here's where things get interesting. The harsh reality today is that pure computational scaling might actually be hitting a wall. Why? Because modern frontier AI, like large language models, requires incredibly curated datasets. We aren't just dumping raw, unstructured data into a model anymore. Today, we're seeing massive investments that heavily rely on human oversight just to prevent these models from generating harmful or completely useless outputs.
The AI community is actively debating the bitter lesson right now because the industry is literally spending billions of dollars just to clean, review, and curate the human knowledge that feeds these massive language models. It forces us to step back and ask, is scaling compute alone actually sufficient, or is human curation an unavoidable bottleneck in our current paradigm?
This timeline perfectly captures what critics call the false dichotomy of the bitter lesson. Just like at chess engines, yes, pure compute and reinforcement learning in Leela Chess Zero initially beat the human knowledge-heavy Stockfish. That happened. But the story didn't end there. Modern Stockfish came back, combined both approaches, neural networks alongside human knowledge, and easily reclaimed the top position. It's a spectrum, not a simple either-or battle.
All right, part 3. Finding new scaling axes.
You have to understand that the frontier of AI is constantly pivoting. When pre-training hits the data wall, researchers move to reinforcement learning fine-tuning. When reward design becomes a bottleneck, they pivot to test-time search, which is exactly what we see with modern reasoning models. And when long chains of thought start yielding diminishing returns, they look toward multi-agent systems. The point is, human knowledge isn't disappearing, it's just continually moving upstream into how we design architectures and objectives.
A perfect example of exploring a brand new axis is DeepSeek R10. DeepSeek challenged the data wall directly by proving you could achieve incredible reasoning capabilities using pure reinforcement learning, completely skipping the supervised fine-tuning phase. Think about that. They didn't show the model human examples of how to think. They just gave it a base model, applied a novel optimization algorithm, and let it discover optimal strategies entirely on its own.
Just look at this actual output from the model's training logs. This aha moment of self-reflection, it was not programmed by humans. It emerged spontaneously. The model actually learned to allocate more thinking time to complex problems and try out different strategies on its own. It's proof that pure reinforcement learning can yield emergent metacognitive intelligence.
We're seeing similar breakthroughs when researchers combine evolutionary search with reinforcement learning, like with the EvoTune method. Here, an LLM isn't just a static text generator. It's continuously refined through RL to discover highly complex combinatorial algorithms, like solving the traveling salesman problem.
It proves Sutton's original point perfectly. Search and learning are synergistic. Search generates the new data, and learning distills the patterns to guide future exploration.
Moving to Part 4, the second bitter lesson.
So, 7 years after his original essay, Sutton explicitly pointed out a massive caveat. Pre-training large language models on the entire internet is fundamentally not learning from experience. It is, in fact, just the largest-scale exercise in baking human knowledge into a system that we have ever attempted. By his own definition, it actually violates the core of his original lesson.
The distinction he's making here is profound. The real world is tremendously, irredeemably complex. True intelligence, Sutton argues, requires metamethods that discover this arbitrary complexity through direct physical interaction. Right now, LLMs are just absorbing shadows on the wall, the bounded text that humans have already written. To achieve real autonomy, systems have to learn their own representations from direct experience.
A really perfect example of this shift is the work being done by John Carmack at Keen Technologies, where Sutton is actually a research scientist. Carmack completely rejected static LLMs. He said they know everything without learning anything. Instead, he's building physical robots that learn to play Atari games using an actual physical joystick. They have to confront all the friction, the noise, and the general messiness of the real world.
The crucial point here is that AI is entering what Sutton calls the era of experience. To keep progressing, AI has to step out of the digital sandbox and face strict physical constraints. Reality doesn't wait for your compute to finish. It's not a turn-based game. AI needs to handle latency, sparse rewards, and sequential lifelong learning, exactly like we do.
Finally, Part 5, Strategic Implications.
Let's go back to that layered metaphor we discussed earlier. Human knowledge never truly disappears from AI, it simply moves higher up the chain of abstraction. In the 2000s, humans hand-designed features. Then that got automated. Next, we designed architectures. Now we're designing reward functions. And looking ahead, human effort will entirely shift to evaluation and alignment. We will decide what good actually means, while the machine handles the raw discovery.
For strategic decision makers and founders, the implications here are massive. You have to resist the temptation to just rely on offline training with static data. The future belongs to experiential learning architectures, systems that are designed from the ground up for continuous, lifelong adaptation in the messy, unstructured real world.
So as we look toward the future, we have to constantly ask ourselves this critical question. The first bitter lesson showed us the undeniable power of scaling compute. But the second bitter lesson shows us that we need to point that compute at experiential learning. Are we just teaching machines what we already know? Or are we truly building systems that can learn how to know? Thank you for joining me for this explainer. I really hope this leaves you with a fresh perspective on the true frontier of AI.